All right, we're about to dive deep, really deep, inside the electronics that run our world. We're going to uncover the two microscopic marvels that make literally everything, from your phone to a massive supercomputer, even possible.
I know it sounds kind of like a trick question, right? I mean, one's just a simple little brick you plug into the wall, and the other, it's a room-sized computational beast. But believe it or not, they share a fundamental secret ingredient.
Yep, that's it. Their entire operation, from just charging your phone to crunching the most complex calculations imaginable, it all boils down to the incredible work of just two tiny components. And stick with me, because by the end of this, you're going to see exactly how they pull it off.
Okay, so first things first, we've got to understand the problem these little guys are solving. It all starts with the power that comes screaming out of your wall socket. And let me tell you, it is not what our delicate electronics are looking for.
So on one side, you've got alternating current, AC. Think of it as this wild, chaotic, oscillating wave of energy. It's fantastic for getting power over long distances, but for a computer chip, it's pure poison. On the other side, we've got direct current, or DC. See how it's just this smooth, stable, clean flow? That's the language our devices speak. So here's the first big challenge. How in the world do we turn that chaos into clean, orderly power? Well, the answer starts with our first little hero, the diode. This tiny component is the absolute key to taming that wild AC power.
You know, a diode is so simple, it's brilliant. Just think of it like a one-way street, but for electricity. Current is allowed to flow in one direction, but it is absolutely forbidden from coming back the other way. It's a valve, and this one simple rule, it's a total game changer.
So if you stick a diode right in the path of that messy AC wave, you can do something called rectification. The most basic way? You just use one diode to chop off the entire negative part of the wave. See? Now we're left with just the positive pulses. It's a decent start, but we can definitely do better.
Now here's the really clever solution, the full wave bridge rectifier. It uses this brilliant arrangement of 4 diodes that doesn't just block the negative part, it actually flips it over and makes it positive too. So now, instead of all those big gaps in the power, we've got this continuous series of positive bumps, way better.
But that bumpy ride still isn't perfect for our sensitive electronics. So next up, we use a component called a capacitor. You can think of it like a tiny water tower. It stores up charge when the bumps are high, and then releases it to fill in the valleys. That smooths things out a ton. And for the final touch, a regulator, like a Zener diode, locks the voltage in at the perfect, stable level. And there you have it, beautiful, clean DC power ready to go. Okay, so we've tamed the raw power. That's a huge step, but just having stable power is only the beginning. To do anything useful with it, we need to be able to control it with incredible precision. And that brings us to our second hero, the transistor. So that's the next massive question, right? How do you get from a simple, clean power supply to something as complex as a computer? Well, the answer is all about control. It's about being able to turn that power on and off, to shape it millions, heck, billions of times every single second.
And for that, we meet the MOSFET transistor, the true workhorse of all modern electronics. The best way to picture it is like a microscopic water faucet, or maybe a dimmer switch for electricity. You've got your source, where the current comes from, the drain, where it goes, and then the gate. That's the control knob. A tiny little bit of voltage on that gate can control a huge flow of current passing through. It's the ultimate lever.
Now, this incredible level of control gives the transistor two amazing superpowers. Let's talk about the first one, the ability to make signals bigger. We call this amplification.
So here's how it works. You take a tiny, weak signal, say from a Wi-Fi antenna or a microphone, and you feed it to the gate, that little control knob. The transistor then uses that weak signal as a perfect template to shape the big, powerful current flowing through it. What comes out the other side is an identical but much stronger copy of that original signal. It's literally like a whisper being used to control a roar.
And you are using this constantly, every single day. Amplification is what lets your phone grab that faint Wi-Fi signal from across the house. It's what boosts your voice in a phone call so people can actually hear you. It's what drives the sound in your headphones. Honestly, without amplification, our wireless world just wouldn't exist.
But that's just its first job. It's analog superpower. The transistor's second superpower is even more incredible. It's what allows a machine to think, using the simple language of logic.
So, an amplifier is like a dimmer switch, right? But what happens if we stop being so delicate?
What if we just slam that gate either fully open or slam it completely shut? Well, the transistor stops being a dimmer switch and it becomes a simple, mind-blowingly fast light switch.
And those two simple states, fully off or fully on, that's it. That's everything we need for binary code. We call off a 0 and we call on a 1. And every single piece of digital information you have ever interacted with, a photo, a song, this explainer right now, is nothing more than a ridiculously long sequence of these little switches being either on or off.
And when you start combining these simple on and off switches, you can build what we call logic gates, tiny little decision makers. Take this NOR gate, for example. You can see right here that depending on whether its two inputs are on or off, it gives a totally predictable output. It's just a simple rule. But, and this is the amazing part, when you link millions and millions of these simple gates together, you can perform literally any calculation you can imagine.
All right, so let's zoom all the way back out. We've got our one-way gates, the diodes, to clean up the power, and we've got our microscopic switches, the transistors, to perform logic. So, what happens when you combine these ideas and then scale it up, like on a scale that is almost impossible to imagine?
You get this. 15 billion. That's the number of these tiny, tiny switches that are probably packed inside the chip in the phone you're holding right now. 15 billion switches all flipping on and off billions of times every single second. Just try to wrap your head around that. It's a scale that's almost beyond human comprehension.
So how is this even possible? Well, the key technology that lets us do this is called CMOS. It's a really clever trick where they combine two different types of transistors that work together as a perfect team. When one turns on, its partner turns off. This simple pairing is incredibly efficient. It cuts down on power waste so much that we can pack billions of them together on one tiny chip without it just melting.
So the next time you swipe on your phone, or click your mouse, or even just turn on your TV, just take a second and remember what's really happening under the hood. Every click, every swipe, every single computation, it's all being orchestrated by billions of these simple one-way gates and microscopic switches, all working together in perfect harmony.
So there you have it. From taming wild electricity to performing trillions of calculations every second, these two components, the diode and the transistor, are truly the building blocks of our modern world. They've completely reshaped our reality. Which, of course, leaves us with one massive question to think about. What's the next building block going to be?